Hi everybody and welcome to another video. And now sit back because today I'm giving a little bit longer presentation of a lecture I just gave this week in the university about AI in astronomy. Now, if you are already tired about all this AI topic, just stay with me just at least for the introduction, because this video is split into two pieces. The first one is a little bit the introduction into AI, and the second part will be about the usage of AI in astronomy. So where I have some selected papers and I will talk about it just afterwards. Now, don't worry, I will not talk about ChatGPT or about other generative AI topics. Okay, there's a generative AI architecture, but not the ones that you are currently familiar with some text prompting or so. I really want to give a very basic introduction into machine learning and also showing you some, classical machine learning algorithms. However, the lecture took only place for, I think, 80 minutes or so. Maybe this video will be a little bit longer to explain some more backgrounds or so. But the thing is that this time cannot cover all the topics, of course. The AI part is a very basic introduction into these things, of course, very simplified also. And also the papers, I will just quickly go through them, but I simply cannot provide all the details. However, if you say, hey, this kind of content is very interesting, it's not so hype driven also, it really actually shows the use case of AI in astronomy and astrophysics, space science, then just write in the comments and I will continue also with this part, giving you more details about certain algorithms, certain methods, or also giving something like updates about papers where I go through certain papers and show you the key insights of the content. However, I would suggest let's switch now back to the to my presentation. I hope you will enjoy it, and let's go. Very well, this is the presentation AI in Astronomy. It's part of a longer session called Astronomy Missions. It's written now here in German. Don't worry about this one. Everything is in English, and it's just an introductory slide or introductory presentation of this topic. Well, before we start into AI in astronomy, I would suggest we start from a historical point of view, giving you a little bit the context how the data grew over time. And for this, I would like to go back to the 16th century. Sounds a little bit weird and strange, but I would like to show you these two guys here on the left, and on the right, we have Johannes Kepler and Tycho Brahe, respectively. And what they did, well, they measured the sky over a very long period of time. In fact, Tycho Brahe, he observed hundreds of stars, I think it was over 1,100 or so, and gave the exact precise positions, and also he observed the planet for a very long period of time. But we will take a look at the original data just in a moment. The conclusions of all the observations these guys had was that Johannes Kepler says, well, he derived the three Keplerian laws, like the law of the ellipses, equal areas, and harmonies. I have some YouTube short videos about this one. I will put the link into the description. And he said, well, everything is basically heliocentric. So the sun is in the center, like Copernicus said, and everything looks very harmonic, so to speak. Tycho Brahe, he disagreed. He was a man of another, let's say, time. And he said, well, the geocentric world is a little bit outdated. So the Earth cannot be the center of the universe. But he couldn't accept it that the sun is entirely the center of the solar system. So he created a mixture of both models. Yeah, so like a Brahe model, so to speak, where he put both ideas of the heliocentric and the geocentric model into one place. Of course, we know now that his model was not correct. The heliocentric model won at the end of the day. However, we have to put everything, of course, into historical context, because at the end of the day, he was also a man of his time, and also, with the corresponding context. Now, Tycho Brahe, he observed one planet in particular, and it was Mars. There we see here the declination of Mars versus the date of the observation. The yellow dots here, they are the actual measurements, while the white line is a fit through all these functions now with our knowledge from today's time, because we actually knew how the position of Mars was during that time. And we see that, well, the the movement changed over time. We have some years with nice coverage, some we have less coverage, and of course, where the declination is too small, it was not possible at some points to observe it. Maybe because also of the weather or so. I simply don't know the context, of course, why we don't have data points for all the time. Of course, sometimes the Earth, the Mars is in conjunction, so it's very close to the Sun if we have it on the other side, so you literally cannot observe it because it's daytime. But anyway, we see that we have a data coverage of over 20 years. And, well, based on these observations, Kepler derived his laws that are very prominent and even valid until this date. Now, the thing is, all the data have been published in, let's say, in books, so not in Excel sheets or CSV files like you would do it today now in some data analysis tools. But we still have some papers from back from 2010, simply called 3 editions of the star catalog of Tycho Brahe, and well, they put some they have some machine-readable versions of it, and in this paper they even compare it with the Hipparcos catalog to see what the differences are. Now you may ask, of course, what does it have to do with AI and astronomy? And I can tell you one thing, nothing at all. Nothing. There's no AI involved, of course, but what we have here is like a very historic case, 500 years old, of big data, basically. Big data, we have only, let's say, a few entries in an Excel sheet. So today it would be just not more than a kilobyte of data, but the analysis took decades and decades for the final scientific insights. Now, with this kind of pace today, we would have been quite lost, because let's take, for example, a modern instrument and also the amount of data it sent back to Earth. In the meantime, while I give the presentation, of course, sometimes I have to take a sip, so I apologize for this. But let's stay hydrated for the lecture. And for this, I would like to take a look at the Cassini-Huygens mission. A mission that I had the very big privilege, I have to say, to work on one of the instruments. It was the Cassini Cosmic Dust Analyzer. I will talk about it later on. Maybe even creating a dedicated video about Cassini. And here we have a poster or a summary of the entire mission that was in the Saturnian system between 2004 and 2017. 2.5 million commands have been executed. Almost 4,000 scientific papers have been published. Nowadays we are over 4,000, I think. Almost 300 orbits around Saturn, 500,000 images, and the 635 gigabyte of data. So, of course, if we take no computational power into our hand, then analyzing this kind of data is like several generations of tasks. So, of course, this shows us that, well, you need, with more data, you need more capacities, more algorithms to work with. Now, for this kind of data here, Cassini started sending us data when AI was not a big thing. So we have, of course, let's say the classical algorithm, the classical ways of analyzing and also processing data. But it already gives you a feeling that, well, the data is increasing, right? Of course, 500 years are in between. But now between 2004 and today, yes, this is a mission that sends us data with an antenna. It's, of course, limited. But other missions, other astronomy-related things are even providing way more data. And for this, we take a look, for example, here to the Vera Rubin Observatory. Observatory that was built in the last couple of years. And I think maybe you have heard about it, also about its scientific objectives, that they want to measure the composition of the universe, like the dark matter, the dark energy, what is the distribution of the baryon matter, and so on. They also want to survey the solar system, so identifying more near-Earth objects, more asteroids, basically building a census of the entire solar system. And then, of course, also mapping our Milky Way. Where are the stars? What kind of populations do we have? What kind of age distributions do we have there? So all these things, and also temporal events. Like, for example, with a supernova, we have a supernova in another galaxy, or some kind of burst event or gamma ray burst, even maybe that could have some effects in the near infrared, would be nice to observe, of course. Now, the Vera Rubin Observatory itself, it has a 8.5 meter diameter primary mirror. It has even a secondary and tertiary mirror system. And it is covering the visible length until up to 1 micrometer. Now, the observatory is in Chile, so it's like around, I think, 2,500 meters. So all the water vapor is not bothering us too much. So we have more better access to the infrared wavelengths. Yeah? So that's the reason why we cannot conduct all the infrared astronomy from sea level, because the water vapor is blocking the infrared light. The other thing is also that the entire camera consists of almost 190 individual CCD sensors with 16 megapixels. Yeah. So if you want to know how a CCD works, it could also be a lecture. Just write it in the comments. And in total, we have 3.2 gigapixel camera, not megapixel, gigapixel. And now imagine we have an exposure time of 30 seconds, recording every day, every night, these kind of images all the time. It is indeed, science. We are doing science in a data age, basically, because this thing creates a lot of data. And now my small question in between, of course, you, the audience, you cannot now interact with me, I know. The question is, how many wait a second, there could also be a method, right, to have some live lectures where I'm talking with you guys about these kind of things. Maybe an idea for the future. But my question in between is, what do you think, how many gigabytes do we cover every night with this telescope? And it's a very tricky question because I frame you with the word gigabytes, but in fact it is actually 20 terabyte of data every night. And it is expected that over the period of 10 years, 60 petabytes are being expected, and around 20 petabytes will be in some kind of catalog database. So all in all, what does it mean? It's a lot of data. It's a lot of data, and we have to process things automatically. On the one hand, of course, to map and categorize known things, and of course finding the outliers for the new scientific insights. Before we continue, the very first image of the Vera Rubin Observatory, this image here of the Trifid Nebula, it's magnificent, right? Thousands and thousands of stars. I could even talk now for hours about this image here, but let's continue talking about now the big data topic, because with all the data we have, 20 terabytes, we have to set the premise that, of course, data processing must be more efficient and more smart in the future, right? Because we cannot handle all the data with, let's say, with PhD students. Yeah? We have to find an intelligent way. And of course, as I just told you, the known structures shall be analyzed in a way so that after all, we have only outliers that will lead to new scientific insights, because we know the known structures like known asteroids, known comets, known planet properties, known galaxies, but we want to see the new stuff. And this all together leads me now to today's presentation about AI in astronomy. Because AI is not the part you know from ChatGPT. It is one part, yes. But AI has a way longer story than that. It even goes back to the 1950s and the algorithms back to the 70s, 80s, 90s, and so on, helping us to analyze the data in a very automatic, decision-based fashion. First of all, AI in a nutshell, for those of you who are maybe not familiar with, if you're a super high-end expert in AI, please forgive me. This is a basic introduction for astronomy students, right? So of course you will say, hey, there are way more things to add. I know. Yeah, just bear with me. It is only covering a fraction of the potential. Now I want to show you 3 domains we can cover with AI. One thing is the supervised learning. Yeah, the supervised learning is like, okay, we have images, let's say astronomy images with stars, with maybe quasars. Yeah, quasars are very active galaxies that may appear like stars, but if you take a look at the spectra, they are way different than stars. Yeah, and for supervised learning, we could, for example, train an algorithm that distinguishes between these 2 kinds of data. Of course, we have training data that is labeled. Yeah, the one has the label quasar, the other one has the label star, so the algorithm knows to distinguish between these 2 data sets. The other one is the unsupervised learning. We will take a look at this. Yeah, we have some kind of data and we simply do not know anything about it. We want to find certain patterns or structures. Maybe we have a few premises to work with, some a priori knowledge that we want to put in there, but maybe not the number of classes. But we will take a look at this later. And another thing is the reinforcement learning. Now, the reinforcement learning is something that is, applies also for robotics, for example, or if you want to write an AI agent playing video games. There's one good example also on YouTube where an AI algorithm has been trained a few years ago to play a Super Mario game. It presses any buttons and then the character dies, and then afterwards the AI gets the response, oh, okay, doing this action led to losing 1 credit in my game, so I have to do something else. So it gets a reward or a punishment based on its actions, and it improves itself over time. If you take a look at robotics, for example, the robot is being, let's say, mathematically punished. It just gets the answer, hey, this was not good. If, for example, it has to learn to walk, and when it falls, it's not good, so it has to adjust its small motors to improve stabilization and the walking mechanism, so to speak. The task that we can achieve is, of course, the regression part. Regression, like, I don't know. I have no astronomy part idea now. Regression task is maybe something like, for example, maybe for a spacecraft, depending on how many hours our engine is running, how much fuel do we have left, for example, right? Also temperature curves or so. The other part is the classification part I just talked about with the quasars and the stars. We have also clustering, right? Like, for example, we have star clusters, we want to cluster them. We have galaxy clusters and so on. Dimensionality reduction is one thing, but this is something I would like to cover later a little bit with generative data, but only on a very, very high level. If you want to get into AI and you are not very familiar with it, just write me. We can add more lectures. I also have some previous videos from years ago where, I just had this YouTube channel here more or less for fun. It's also about talking about data processing, parameter tuning, of course, and also how to train a model and also how to select the perfect model at the end of the day. This is nothing we can cover today. I just want to give you the awareness that these topics exist. And if you watch any influencer talking about the best prompt and what have you, it's all about inference at the end of the day. But the real magic is creating your own neural network, creating your own training scripts, preparing your data perfectly to achieve what you would like to have. Let's go to the very first algorithm I would like to talk with you, and the algorithm is called the support vector machines. SVM was introduced in the 90s, and I would say let's take a look at data in 2-dimensional space. This algorithm works perfectly also in 20 dimensions, any dimensions basically. And we have 2 data sets. One has the class -1 and the other one +1. I don't know what kind of data, some tabular data, maybe even stars on an image, for example, or something like that. Maybe some housekeeping data from our spacecraft that gives us some insights about its current state. Now the question is, we have a new data point here, and I would kindly ask you, where would you assign this data point, right? Of course, intuitively you would say, hey, of course to the right side, not to the left. Just draw a line in between and we are done. But I could draw a line like this, right? And then the blue one would be assigned to the -1 group. And of course, intuitively, you would say, that's stupid. It doesn't make sense. The line has to be set somehow differently. But what does it mean setting it a little bit differently? Well, for this, I would suggest we draw a thick area in between. And what I want to do in support vector machine algorithm is I want to maximize the size of this area. So maximizing this distance between both sets of data. And for this, well, you have to write down some kind of, what is the English word for that? So you have to write down the conditions, and then with a partial differentiation, you get a set of equations you have to solve with Lagrange multiplicators. It doesn't matter for today, maybe for another video. And then at the end of the day, you try to optimize the maximum margin between both sets. And this leads, for example, in this case, to this kind of area. And if we squeeze it now back to the center, we have now our separating line. And the 2 points I just colored, they are the so-called support vectors. They support, or they set the limit or the position of this area that creates the classifier, the separation. In 2D, it's very simple to visualize. In 3D, you can even imagine. Things became complicated in 3, 4, 5, no, in 4, 5, 6, 7, 10 dimensions. But the cool thing is support vector machines, they work there. And with the current computers, yeah, you can really do it quite quickly with small data sets. Just try it out. I will talk about it later, what kind of libraries you can use to have a look into this. Now, the thing is, though, that support vector machines, there are way more than that. So, for example, you want to write a line or an area to separate these two data sets with a single line. It doesn't work, but you can apply the kernel trick to increase, let's say, the dimensionality of the two classes, and then you can draw a line in between. Now, if you're interested in more details, I strongly recommend you this book, Support Vector Machines. I'm not paid by any, by the way, there's no payment involved or advertisement in this lecture. Just my recommendation, because this book here gives you all the details for support vector machines and other kernel-based learning methods. However, this book is also very difficult sometimes, mathematically speaking. So if you are more interested in applying these things, I recommend you the corresponding libraries. Let's take a look now in some unsupervised learning methods. And for this, I created 700 data points here. And we will do something that's called the Gaussian mixture model. And my first question to you is, now in my lecture, of course, I talk with my students and ask rhetorical questions, or even sometimes setting some traps. How many clusters do you see? And of course, it's very trivial almost. You see 3 clusters, right? We see somehow three centered areas. In 2D, it's simple to see. In 3D, even maybe. And again, in higher dimensions, these becomes more difficult. But let's set the premise. We know we have a lot of different data, and they are somehow described by Gaussians. Now, how can we maximize, or how can we compute the Gaussians here? Well, if we take a look at the likelihood of models, things become a little bit weird, because here on the right-hand side, we have in the sum, shows us the sum of all the different Gaussians. So we have the sum of pi k times n, and n is just the normal distribution in n-dimensional space. Don't care, just look at the n. And we have pi as a scaling factor. And the thing is, if we want to maximize the likelihood of if we want to maximize the likelihood, what we have to do is we have to draw 700 individual Gaussians, because if every data point is in the center of its Gaussian, the likelihood is always 1. And then if we multiply all these ones together, this big pi symbol, then we get 1. We get the highest likelihood for a model. So very cynically speaking, you can say, hey, drawing 700 Gaussians is the best model. Well, of course, intuitively, as a feeling, it's just a feeling, it feels wrong, right? I don't want to draw 700 Gaussians. It's completely insane. It goes into the direction of overfitting. So highest likelihood for 700 individual data points, 700 Gaussians. Somehow it doesn't feel right. And for this, we have something from the philosophy almost. It's called Occam's razor. And Occam's razor in Latin says, let me pronounce it in Latin, entia not sunt multiplicanda praeter necessitatem. Which means in English that the entities should not be multiplied beyond necessity. Or, speaking in our AI world, one should prefer the model that explains the data well with the fewest necessary parameters. Now, if you are, let's say, sitting in a rural era and you hear horses walking, you think about horses, you don't think about zebras, right? Because it's more likely that if you live in the UK or Germany, that outside we have some horses running around and not zebras. So the zebra would also explain the model, but it needs more parameters, because it would be kind of strange to have free roaming zebras in Germany, UK, or whatever. Anyway, here in this case, we want to have a model that has a certain complexity, but that also has the fewest parameters. And for this, we use, First of all, we simplify our likelihood, just write it down with the L hat at the bottom. And now we go to something that is called the Bayesian information criterion. And let's go through this equation together. You see the L hat on the right-hand side. This was our likelihood, the complex formula in the beginning. And what we see here is the likelihood L. We have N, which is the number of data points, in our case 700. And K is the number of parameters that you need to describe the entire model. Yeah, so for example, a single Gaussian has one mean and one standard deviations. Two Gaussians have two means and two standard deviations, and so on. Yeah, for multidimensional Gaussians, we have even more, yeah, like the covariance matrix and so on. But let's stick with this picture. Now, what happens with the Bayesian information criterion? First of all, we introduce more complex Gaussians. Yeah, we improve. We take a look at this data. We make one Gaussian, then two Gaussians, three Gaussians, and so on. And the likelihood increases because the right part increases very, very well. And the left part is also increasing, but maybe not so well as the right-hand side. So the likelihood is increasing way higher than the, let's say, complexity term in the beginning. Now, at some point, we have a minimum. Yeah, the likelihood is so good with the number of parameters that we have a Bayesian information criterion minimum. At this point, we have the perfect model. Now, if we increase the number of parameters, the likelihood is maybe not that much improving anymore. Maybe just slightly, right? Because, well, here in this case, having three Gaussians maybe is even sufficient enough for the entire data to explain the entire data set compared to 700 Gaussians. But on the other hand, 700 Gaussians lead to a higher K value on the left-hand side, which means that the Bayesian information criterion at the beginning, hopefully, will decrease and at some point increase again because it reached its minimum, its best value, and is worsening afterwards. So what does it mean in our case? Well, this is actually done with Python. I did the Bayesian information criterion computation for different Ks, for different number of components simply. And I found a minimum at 4. Okay, cool. Of course, I know it's 4, right? But anyway, stick with me. Now we have 4 Gaussians, and then we can compute the probability for each individual data point and assign it to a Gaussian where we have the highest probability, and then color code it. Now let's get back to our data set. If we color code it, then we get this kind of distribution. And this is interesting because I actually did this. I had a 4th Gaussian in the background that was creating some kind of a background noise, yeah, the blue dots here in this case. Yeah, because with the human eye, you simply cannot see if the dots to the outside are coming from the same distribution. Yeah, it's very difficult to see if this exponent, if the decreasing probability is linked to this Gaussian, but in fact, it's not. Yeah, so this helps us, and with this unsupervised method, to find maybe unknown structures in the background or to distinguish between certain structures, which is pretty fun, I would say. It's a very mighty model. And of course, in higher dimensions, it's even more useful because you don't have any help to visualize the data properly. Now, there's one library called scikit-learn. Highly recommend the documentation and tutorial. And they have this funny, yeah, take it with a grain of salt, of course, algorithm cheat sheet where you start at the top. And then you have to see what is your task you want to achieve. And then they give you some hint where you can go from the algorithm wise. So the algorithm here is colored in this green color. But let's continue a little bit regarding machine learning, because I would like to recommend you the machine learning Bible, so to speak. It's called Pattern Recognition and Machine Learning by Bishop. And this book here is like, I think it's almost over 20 years old, but the classical machine learning algorithms, they are described very well in there. And I have to tell you one thing, if you go through the entire book and you write me in the comments and say, hey, Thomas, I wrote the book and I understood everything, you will get 2 reactions from me. First of all, I will say, whoa, impressive that you had the time. Second of all, I don't believe you understand everything. It's really a crazy book. It's impressive. Yeah, but jokes aside, yeah, take a look at it. It's really impressive. Now let's go to the neural network part, and I cannot cover all the parts. I simply can't because this topic is too complex to cover everything. So I apologize for that, and I will simplify things. Yeah, I will simplify them. First of all, we have inputs in a neural network. Inputs like a vector, for example, a tensor, a matrix, anything, yeah, shown with the x1, x2 until xn. Now we multiply this with some weights, x1 times w1, maybe plus a bias value plus b, then x2 times w2 plus b, and so on. And then we weight all these multiplications and put this into an activation function. The activation functions look like this, like the rectified linear unit in the top left, or the leaky ReLU, or the tangent superbolicus. It really depends on the task. And then at the end, you get something like an output. For example, a classification, a regression part or so. What happens is you want to adjust the weights W1, W2 into a fashion that, based on your training data, let's say 50 images of galaxies and 50 images of quasars, you want to have the best success rate in regards of classification. Classification is being conducted or shown by the output, the y hat. Now, of course, in the very beginning, when we initialize the network, yeah, so the weights have random values, we want to adjust the weights into a fashion that improves the mathematical equation in such a way that if we put the training data in the left-hand side into the model, that we get the correct y values. And for this, there's a method called backpropagation, where the error, the corresponding error, the expectation, the difference between the expectation and the reality is sent back into the network from the right to the left to improve the weights based on differential derivatives. Maybe a little bit too complex for today. I cannot cover it, of course, right? There are also a lot of other YouTube videos showing it, but maybe for astronomy context, I will give you another lecture on this. What's important for you to know is we have a collection of a lot of functions working together to create an output. Now, the error, the so-called loss, depends really on the task. We have, for example, the mean square error. Yeah, maybe you know it from simple regression parts where we simply compare the y values. Yeah, the true value minus the expected value square rooted, normalized. We have also the binary cross entropy. This is basically used for two class classifications. So y and y hat, where they have either 0 or 1 or -1 and 1. And we have also the KL divergence that is being used, for example, for generative AI. But we will not get into this. I just want to give you the feeling or the idea that different loss functions are being used to show the difference between the expectation and the reality, so to speak, and then being used as an input to improve our model. Improving means that in some weird hyperdimensional space, we have a starting point. The starting point here you see at the very top. And we want to improve the weights in such a fashion that our loss function minimizes at some point. So we search for a global minimum. And there are certain ways to do this. Yeah. So for example, you can imagine you have a sledge. Yeah. This is like a snowy mountain and you want to ride the hill. Yeah, there is, like, for example, in the beginning, you see there are less differences. Yeah, so maybe you increase the so-called learning rate, so you make larger jumps because you don't want to spend too much time working on it. And if you go down in a very steep slope, you want to have smaller steps, yeah, smaller learning rates, because you don't want to overshoot or you don't want to get stuck into in an area where there's no progress at all. You really have to, you can adjust dynamically the movement, let's say the path in this hyperdimensional plane. Very difficult maybe for those of you who have never heard about it, but yeah, again, I think you get at least the idea. Now, if we train our model, you have your data set mostly separated into a so-called 60-20-20 fashion or 80-10-10, which basically means that you use 60 or 80% of the data for the training purpose, 10% for the validation. So in real time, let's say you compare the results with the validation data. So the validation data is not being used for the training of the weights, but to compare the loss function, the loss results. And at the end, if you have your final model, you use the test data to finally check how the final results look like, because with the validation information, you also, let's say, spill in some information in the training process. So at the end of the day, if you use different training steps, you start in the beginning and you iterate for several so-called training steps, or epochs as it's called, your loss function should improve. Yeah, so the blue one is the training data. It improves most likely into infinity, or not infinity, for infinite steps it goes to 0, but it overshoots, so to speak. Yeah, it at some point you learn literally the training data, but what you want to have is you want to have a generalized concept. So what I want to say is, if you take example images of cats and dogs, and your dogs are mostly huskies playing in the snow or pulling a sledge, then at some point the model will associate snow and also sledges with dogs, right? But of course, a dog is a more abstract concept than a husky pulling a sledge. Which means that if you have the validation images of dogs, at some point you will have a minimum, so the model understands the concept of dogs, but at some point the model misinterprets the concept of huskies as dogs, which leads to the weird shape or to the weird behavior that the validation error afterwards increases again. So you want to always find the minimum. If you do this in Python, you can simply check. It doesn't always happen like that, but this is like, let's say, the perfect case example. If you want to play around a little bit, you can go to playground.tensorflow.org, and I would suggest let's go there and see what's happening. And here we are, and let me just see, I'm covering some parts I have to hide. Anyway, and I want to have here, I have a classification problem, for example. I can adjust a lot of different things, like I showed you the activation functions and so on. I can adjust the number of neurons in between and so on, so I have an impact about a lot of stuff. And when I click on the play button, I will train for several epochs to see if I can distinguish between these two data sets to create a classifier. The support vector machines I showed you, I have to, let's say, increase the dimensionality to draw an area in between. But here with neural networks, let's click on play button. You see the training and the loss functions, they are improving, and they find some kind of shape. It's not like a perfect circle or so, it looks like a hexagon. But this is the perfect result. You may ask yourself, why is the validation error not increasing? Well, maybe the validation data is also pretty straightforward, like in this case, so it's not like so difficult to distinguish then, for example, a husky and a dog, as I just mentioned before. What you can do here is also you can increase the noise a little bit, so you see the blue and the yellow dots, they are mixing together. Let's remove maybe some hidden layers, so we have a very small neural network, and you will see that maybe it takes us some time, or it will never reach to the point of generalization. So it's too abstract, this concept, for this shallow network, because we don't have maybe enough neurons. So we can add more neurons, for example, so we have more information that we can put into the network. And let's see if this helps. And we see that here we found a classifier. The test loss is higher than the training loss, but well, it's just here a concept, and I would suggest play around a little bit and see how this model behaves. And we are back here in the neural network part in my presentation, I want to say, and I would like to go into another part, namely the dimensionality reduction and generative data. Now, if you say, oh no, I'm out, I don't want to talk about ChatGPT or so, stay with me, because the architecture I want to show you, well, I created a video about this very long ago. It was like a project, it's a playlist, I think, but maybe I should re-improve it. So first of all, let's take a look at this image and stay with me. We have on the left-hand side images, like for example, this noisy image of numbers. On the right-hand side, we have the good images, or we have just simply the same thing. So what we have is we have data, put it into a neural network, and we want to have the same result again. Sounds a little bit weird, but take a look at the structure in the middle. What we have is we have some kind of compression. So we compress, let's say, 100 times 100 pixels, for example, to 10 neurons in the center, and then we expand it again. So it's like compressing data. The compressing part is called the encoder, the decompressing part is called the decoder, and in the middle we have something called the latent space. Now the latent space is something that contains the compressed information of the numbers. Let's take an example. you want to describe yourself on a selfie. Your selfie has 1,000 times 1,000 pixels. You would never have the idea to describe each individual RGB value of the image, right? It wouldn't make sense to describe 1,000,000 pixels, because you as a human, your face has certain features, certain facial features, like for example, the size of the nose, your the length of your hair, your skin, whether you may be wearing glasses, or the shape of your ears. So you describe yourself based on these features. And this is what the autoencoder basically does. It compresses the information into something that contains the features of it. Now, if we replace this latent space, for example, by a mixture of Gaussians, so to speak, like sigma and the means, and based on this distributions, we sample data points out of it, we can generate new data based on that. Yeah, so we train a model with different faces and different emotions, and then we choose some points in this latent space and put it into the sampler. We can create new artificial faces, for example, or faces between two faces, like we see here in this example, in a low resolution case where we have, like, let's say, a latent space walk between different faces. Now, why should this bother us? Well, in astronomy, we can basically do the same thing. We can take galaxies as an input, put it into an autoencoder, and based on the features, we can do some statistics about the feature distribution of the galaxies. Yeah, so one feature could be the number of arms of a spiral galaxy, the brightness, the size, the number of young stars, and so on and so forth. So the autoencoder helps us to compress data into a feature space that we can work with later. Now, if you are interested into the most recent AI hype, of course, ChatGPT, Gemini, and what have you, I would suggest to read this paper called "The Attention is All You Need." It's like the Gen AI Big Bang, where the guys from Google introduced a new mechanism, new layers, let's say. It's called basically attention. And this was like the starting point for all the big models we have today. Yeah, but this is not the only thing, the attention layer. We have a lot of things. Convolutional neural networks, unit architectures, mixture density models. I don't know, transformer, which is based on the multi-head attention, based on the attention, temporal convolution networks, and so on and so forth. A lot of different architectures, a lot of different structures, activation functions, ways to train these neural networks. All in all, as a ChatGPT user, you don't see these parts, right? You don't see the background. You live in a house without knowing how the house has been built. Of course, you don't have to if you simply want to live in the house. But if you want to know how things work, I recommend you to go through these things. If you are interested in learning deep learning, yeah, with Python, I recommend you this book by François Collet, the 3rd edition of Deep Learning with Python, the most educational, valuable book I've ever read in deep learning. It has a dedicated focus on keras. I will talk about this later. One of the best books out there for deep learning. Believe me, it's, for me personally, it was a game changer in understanding it. And I think I even I read it 3 times basically. The 1st edition, the 2nd edition, and now the 3rd edition. It's cool. Again, I'm not getting paid by anybody, not by him or Manning or so. Just a recommendation from my side. I think I talked now for almost 45 minutes, and it's time now to go to AI in astronomy. Now, if you just skipped all the parts beforehand, you don't want to know anything about the AI part, just go a few seconds back. I made some book recommendation, but anyway, let's go to the first paper I prepared. And it's called Identifying Exoplanets with Deep Learning. Now, this thing is something I would suggest to go first and talk about how exoplanets are being identified. There are different ways. And one of the ways to identify exoplanets is the transient method. Now we have a star, and then a planet is moving in front of it, and it's causing like it decreases the brightness, of course, for a certain time, and then afterwards it increases. Now, what the guys in the paper did is they had a lot of different curves for this. Yeah, they called it on the left-hand side the global view, so the entire recording. and the local view, the part where we have some transit event. Now, this doesn't even necessarily mean that an exoplanet is really moving in front of it, because stars behave weirdly. Some stars, they have maybe changing brightnesses because of their properties, or there are even dust clouds or other effects that cause the decrease of the brightness. So what they did basically was they wanted to train a neural network out of this, on this global views and the local transit events, how they called it. So they wanted to differentiate between all the different effects, of course, and for this they used around 15,000 events from the Kepler mission. For this, they took the part into a convolutional neural network, like separated into two branches, and were training the model. And at the end, they found that the detection performance improved compared to human experts. So they, I would say something like blind studies, right? They wanted to see how their algorithm improves, or is it comparable to the performance of human classifiers, and it was even better, especially in the low signal-to-noise ratio domain. And this was even a few years back, so probably it improved even better. They found new planets, like for example Kepler 90i, English language, which was, I think, a solar system where 90i was the 8th planet of this solar system. So it was the first solar system outside our solar system that also had 8 planets. So a big deal, I would say. Future work, we have to take a look maybe in the other papers to see where the status is now. But now on the right hand side, I was talking about convolutional neural networks, and I would like to talk about this just for a few seconds. So convolutional neural networks are like networks where you have a small, something called a window, and this window is moving along, for example, a picture or signals, and is extracting feature out of it. And the deeper the neural network, the more features it can extract. So let's say for this part here, the robot, in the first layer, it identifies, let's say, dots and lines and stuff like this. In the next layer, based on these lines, it identifies then, for example, the shape, a circle or a square or something like this, a trapezoid. And then the next layer, it combines these figures together and says, okay, this looks like a head, this looks like an arm, and so on. And with the deeper layers, it then at the end, classifies it, whether this is like a human, a horse, a cat, or in this case, a drawing of a robot. The next thing in AI and astronomy is gravitational waves. So this is the LIGO observatory. These are like two arms perpendicular around 4 kilometers length. And what they do, basically, they shoot lasers into both directions, and when they receive both lasers, they expect an unchanged beam of this laser. So if nothing happens, they have a certain pattern they expect how the laser should look like. However, if you have an earthquake, perturbations, a truck passing by or so, or gravitational waves, then this pattern changes, of course. The big problem, though, is that the gravitational waves, the effects of gravitational waves in our space-time continuum, have a way smaller effect than, for example, an earthquake. So they wanted to use AI to improve it and detect these gravitational waves. And for this, they published a paper in Physics Letter B back in 2018, and they were kind of successful. They, first of all, had something called the classical way, with so-called match filtering between data and a database of templates. And then they used the convolutional networks as well to determine gravitational wave events and also derive parameters that led to this wave structure. And why did they want to do this? Because the template match filtering is like, you can imagine it like a database where you have templates of how does the structure look like for an earthquake, for a truck, or what have you, and what are the expectations for certain gravitational events. And this match filtering, you can imagine if you have more and more templates, the computational time increases. But if you train a neural network with all the templates, you simply have all information inherently stored in one neural network, and you can just have to conduct one computational execution. And they found basically a lot. Yeah, they even said that it improved and the detection, and the authors were able to achieve something called sub-real-time analysis. Yeah, so the analysis was even better, or was faster than the real time. Yeah, so let's say if the AI would need 2 seconds for 1 second detection, for 1 second recording, it would take, let's say, increase the data size over time. But here they were able to analyze everything with AI in sub-real-time time. The next part is something using foundation models in astronomy. With foundation models, I mean talking about ChatGPT or Claude, or in this case, also one of my favorite models, Gemini from Google. Now, what they did is they actually wrote a paper, and it also went to Nature Astronomy. And there's also a nice Google research blog post. I will put the link in the description. They wanted to use reference images of supernova, like for example here on the left hand side, supernova, non-supernova, put this into Gemini and tell it, look, this is how a supernova looks like. This is a good reference image, you know, giving it all the descriptions in a human readable fashion. And Gemini, they revealed them. It was like a supervised classifier. It said, well, whether this is a real event or not. It even gave some kind of confidence. It called the interest score. They said, Gemini said, yeah, this is a high interest event. And then also an explanation. So it even not had supervised capabilities, and also some kind of providing metrics, but also giving explainable AI capabilities. This is important because if the AI makes a certain decision, you want to know why. Why for a certain case did the AI make the decision? And Gemini was able. It just says, draws, maybe gives you some information on the image. Here, this is the part that led me to the decision that is a supernova. And you see, for example, here in the explanation, the image has a bright circular source at its center. In the reference image, there's no source in the center, but a galaxy can be seen on the left. The difference image shows a positive circular source, as would be expected for a real transient. Transient sources can occur on top of the underlying galaxies, such as a supernova in a galaxy. Yeah, so it's pretty nice to see that it's even able to explain what's happening. Now, if you're a scientist and you say, oh, wow, okay, my job is now really, yeah, I think I will lose my job as a scientist. Don't worry. Because the thing is, Gemini helps you, or this foundation models help you in really doing, let's say, I don't want to say the boring task, but the survey part. Yeah. As a scientist, you don't want to sit there and analyze all the images all the time, tedious work. You really want to have the process data on some high level state, so to speak. Yeah. And go from there and derive conclusions. For example, yeah, prove your theory, deny your theory, derive new conclusions, or find outliers in this. It's not like that these foundation models will be like big agents conducting science all the time. Yeah, you want to, as a human, do something new and not simply write paper for the purpose of writing papers. Yes, there is a pressure, but my personal hope of using these models is that, and this is just my personal opinion, that the quality in the scientific community will increase, yeah, because people will spend more time in the outliers, in the scientific insights, in the new part, and not, by all due respect, describing the next exoplanet system or so, yeah, and just filling papers because they have the pressure to publish. I hope these kind of models will help us improving the quality of the paper, so that we reduce the quantity a little bit, because sometimes the quantity is a little bit overwhelming. It's not only in AI, it's in every scientific domain that is overwhelming. Again, just my personal opinion. Let's get into the statistics from table 1 here from the paper. For different telescopes, we have here the accuracy, precision, and recall, and it's pretty impressive to have to say. You don't have to train a model, you just let's say in quotation, you simply use Gemini. And we have here just a small reminder for you, what is the accuracy, precision, and recall. So for example, the precision is the ratio of the true positive, so the true, actual, real supernova, compared to the set of true positive and false positive. So let's say we have here the precision of 95% for Pan-stars, which means that out of 100 supernova classifications that were provided by Gemini, 95 were real supernova events, and the 5 others were false positive. Maybe some other events, maybe I don't know. Yeah, I haven't seen the data, of course, but maybe let's speculate, like hot pixels or other events that were causing the wrong classification in this case. Well, let's go now into my work, what I'm doing, and it is the Cassini Cosmic Dust Analyzer. Now, for those of you who don't know about the Cassini Cosmic Dust Analyzer, I will do a dedicated session about this one soon. The most important thing is, however, that, for example, we have a lot of science and nature publications here with this instrument. You see the opening is around 50 centimeters, and what you can measure the chemical composition of small dust particles, or we were able to do it in the Saturnian system. And we can now we will use AI now, for example, to recalibrate the instrument. I'm currently doing it. I'm writing a paper, and I think it will be published soon. I will talk also about the paper in the future, because then you see also my work, what I'm doing, and we will rewrite the science and go through the science I was doing it. But, well, this, unfortunately, a little bit the science, I have to be a little bit careful not to publish everything now, because I want to have also the publication done with the new method I'm currently working on, also an AI method. We want to conduct some supervised classification of the mass spectra. Don't want to go too much into details, but cool stuff is coming. I have 2 students working on unsupervised classification of the mass spectra as well, also very cool, and more things to come. Now, if you are interested into astronomy, Python, and AI or machine learning, there's one great book recommendation. It's called Statistics, Data Mining, and Machine Learning in Astronomy. This is an updated version now. I think this is now the second edition. And I really recommend you also this book. It provides you with everything: astronomy background, statistical background, machine learning background, Python code, some plots, and everything. And the cool thing, everything is in Python, and they have even a dedicated library called AstroML. And in AstroML, you simply can go there, watch, take a look at the book figures or so, and then decide for yourself if you would like to work with on this book or not. In regards of machine learning, we have scikit-learn, and I also recommend you for beginners to use Keras, because Keras is like a high-level API for TensorFlow, PyTorch, or JAX. Yeah, so if you hear some AI people say, yeah, I use always Torch, it's the best one, and so on, I don't know. I mean, TensorFlow is also a very mighty tool, I have to say. I didn't work a lot with JAX, so I can't tell you anything about this. If you are an AI researcher, you will not watch the video, right? But if you are an astronomy student or so, I will simply recommend using Keras. Yeah, the thing is that in PyTorch is used by AI engineers and AI scientists, because you can adjust and tweak a lot of different parameters for your own work, really make it maximum customizable. But for your work as a student, for example, or even in a PhD, you want to create machine learning or models that classify your data, that make a regression or so, and you don't need any costume loss functions in 99.9% of the cases. You need the basic stuff, the layers that exist there, and Keras provides you with everything. Just my recommendation. If you want to have a look at the most recent models in the open source community, I can really recommend you Hugging Face. Take always a look into Hugging Face. GitHub, of course, for the code Hugging Face for AI models. And some other key skills for AI that I would recommend, but now it's a little bit difficult because you have to be careful regarding the costs, is of course learning a little bit cloud usage. But yeah, the costs can really be a big trap. Also the same thing also for European clouds like Scaleway. Yeah, you have to be always careful. But things like Runpod or Google Colab give you the opportunity to really, for Colab, for example, you simply pay a certain amount and then you have some cloud service, rather simple, but you can use some GPUs, some tensor processing units. And with RunPod, you can run your own Docker containers, right? You simply load, let's say, $50 from your credit card, and if it's depleted, then the server will turn down. Yeah, so you, as far as I know, so you will not fall into some kind of financial trap in this regard. Last but not least, if you want to go deeper, I also recommend you to get into machine learning operations, ML ops, yeah, something like that, so that you really get an understanding how models have a life cycle, how models are improved in real time in production and so on. But all in all, I think this is all I wanted to share with you today. Thank you very much for watching. I hope you enjoyed the small lecture here. I think it was more than 50% of AI, but hey, I think it's okay. If you like this kind of topic, if you like also the kind of lectures, also with scientific background or so, you want to know something about a paper, just let me know in the comments and we can also do this one. Otherwise, the next videos will also be again about Universe Sandbox, some Python coding, and all the stuff I like in astronomy. And in the meantime, maybe there will also be coming a second channel where I will conduct some more fancy, funny experiments with Universe Sandbox, because sometimes I lose some time in the evening playing around with this one. Anyway, I hope you learned something. I wish you a nice weekend and see you next time.